All right, I'd like to welcome everybody to the collision repair and refinish stage at the last day of SEMA 2025. And we're going to be going over some things with car aligner and welding in today's collision repair facilities with equipment that meets OEM requirements. So Jeff, why don't you give them an introduction and we'll get started.
Okay, well, thank you. Go through the iCar slides here. Okay, so I'm sure you've all heard the phrase, always follow OEM procedures. So unfortunately, due to the accident in Texas several years ago, it's something that was brought to the forefront. The importance of that, there's lots of discussion. We have lots of advocates throughout the industry that have pushed that, not least of which being iCar, how critical it is that we follow that OEM repair procedure. And it only makes sense. The OEMs are the ones that have the materials, they know what's been used, they have access to all the original design data, they have the collision testing to prove their repair procedures. Every year in Detroit, they hold a conference, Great Designs in Steel, and it's interesting to see a 5-year plan to design one, B-pillar. So it's just...
That is one show that when the engineers are, I know they're speaking English, but I understand about every third word.
Exactly.
But it's amazing how much actually goes into every single part on a vehicle, especially the structure, the glass, and following those OEM procedures is so critical because you can do a process, but if you don't do all the steps, all the basic things right, the whole thing falls apart.
Exactly. So carrying that forward, what about OEM approved equipment? So we're saying we need to follow their process. What's the importance of having the equipment? So OEMs generally go through 2 different processes. A lot of them do testings. That could look several different ways. It could be providing samples that are then destruction tested. Could be taking the machine themselves. Various ways of doing it to guarantee that it's going to perform. Other OEMs go through a specification, looking at what the requirements are to make sure the equipment meets it. In either case, they're going through it to verify it's able to do everything in that repair, just like the repair procedure that it needs to do. So despite that, we still get conversations all the time. Well, I have this unit because it's required for the program, but I'm used to this other one. Well, I've got that one, but why can't I use this one? So, the question is, okay, well, spot welder is a spot welder, isn't it? Of course, the answer is no. So the basic technology is the same. So back in 1886, Elu Thompson came up with the theory, got the first patent. The theory is the same, but we've gotten a lot more sophisticated about it and how we manage things. So when we talk about welding, we talk about weld current, weld time, and this grease pressure. So those 3 things are critical to making a good weld and guaranteeing we get the fusion. So one of the nice things about it is if we look at like a thermal graph here, you can see we're at almost 3,000 degrees in the center there for the nugget where we get fusion, and 5 or 6 millimeters away, we're down to 80 degrees. So it's one of the benefits of spot welding is controlling that heat. But that's also something we need to look at as part of the repair. So when we look at the parameters, it's pretty obvious, okay, if we don't have the parameters correct, we're not going to get the fusion that we want, okay? So 10,000 versus 8,000, we don't get that fusion. But when we talk about welding, it's not just about the weld nugget and making sure we get fusion. We also need to look about the heat effect zone. So when we talk about new materials, particularly high-strength steels, ultra-high-strength steels, they're all very heat sensitive. The way they manufacture them, we're trapping that carbon. If it's not managed correctly, we can damage the structure of it and the characteristics, so it won't perform correctly in a weld. Okay.
I think that's something that, all those very specific parameters at the OEM, some of them call out very specific, parameters for this weld. You need to have this much clamping force. And I think one thing that people often will overlook is the spot welder has, it can do this at this rating, but what's the PSI at the shop and all those kinds of things. And that's something that I think not enough people pay attention to.
Correct. So one of the things I wanted to point out, when we talk about fusion, it's all about energy. So when we're looking at weld current, weld time, and that pressure, together that's a certain amount of energy. So you could do one weld at 10,000 amps, so many milliseconds, and get a weld. You can do another at 5,000 amps at a longer time and still get the same nugget, but the problem is now we've created a worse heat effect zone. It's longer for that heat to spread out, damage the surrounding metal that could end up damaging the metal and not have it perform the same during a crash. So when we look at some of the specifications that OEMs consider when they're doing their testing, so like the maximum weld current. So we have machines now, 16,000 amps, 1,430 pound force. It's guaranteeing that we have the capabilities to handle those new materials, and in a lot of cases being able to get in, do the weld quicker, and not damage the surrounding metal becomes the key there.
Yeah, and I think it's interesting because you have the main power, the three-phase power. We had an entire panel discussion earlier this week on what happens when you don't have enough power coming into the shop and all the different things that you can do to get the power up in the shop and how critical that is. You can have the best machine in the world. If it's starving for power, it's not going to be able to do all the things it needs to do.
Absolutely. So a lot of the welders nowadays are inverter welders. So we're taking an AC input, converting it to a DC. We're also changing the frequency. A lot of people don't realize that. So instead of 60 hertz or 60 times a second, we're at 10,000 hertz. What that does is it gives you a nice, clean power, and we can apply that energy quickly and do the weld. And the main power does come into play. So if you're trying to use a single-phase welder, and it maxes out at 6,000 amps, so now we've got to make a long weld, and it's greater risk that we're going to damage the materials. So, absolutely. Okay. One of the other things that has become more and more prevalent is smart welders, and a lot of the OEMs have gone this route. So a smart welder has the capability, it's going to determine the type of material in that and set all those parameters for us. Generally, we start with some type of a calibration that's letting us verify the system is good and ready to go before we start welding. Then we go into a mode where we can weld. It'll identify the thickness, the type of material, set the parameters, realize if there is some type of contamination that we need to burn through, and add a pre-pulse, so all of that. So in a lot of cases, smart welding is what the OEMs are looking for and aren't looking for anything that's not. Okay. However, there are other OEMs that prefer to go a manual approach. So for example, Honda has their weld matrix that they've created. They looked at all the materials, came up with time, current, squeeze pressure that they wanted to guarantee a weld in each of those scenarios. And as you can see, their repair procedure would actually call out this many of weld condition 13. So to accommodate that, welders also need to be able to run in manual mode, where we open it up that we can do time, current, squeeze pressure to set according to the OEM spec. What we've done with CTR9 is we've gone ahead and taken that and added it in so they can select it, and that weld condition will then pull up and we can weld right off of it. But the important thing is the machine has to be capable of handling it whichever way the OEM requires.
Yeah, and I think that's something that has really been an evolution to where they're calling out specific weld parameters, and now you have pre-programming. So it always takes some time to get that built in, but it's great to see that those improvements are being made, because setting that each time and changing it for all the different parameters, it can take a little bit of time, and if the technician's not very good at it, where they can just select that program, it saves them a lot of time, and it's set up the right way each time.
Absolutely. And the other thing is programmability. With the technology we have now, as new materials come out, as new procedures are available, machines can be updated and adapt, which is really what we need to do, is to be able to keep up with the developments that are happening in the industry. So the other question is, what about MIG-MAG? I mean, surely it doesn't matter. It's a MIG welder, it's a MAG welder. What are we going to do? And the answer is it does matter. So with MIG-MAG welding, the biggest thing is transfer modes. So traditionally, when we're talking about steel, we're short circuit. wires coming out, touching. When we look at aluminum and silicon bronze, because they're so heat sensitive, we're using a spray pulse. So the wire never actually touches. We got a background current that keeps it running, and then a pulse that lets us clip that droplet and throw it across the arc. And the benefit is the average of those two is less heat. So when we're talking about, like Honda, their 1500 megapascal door openings, if you can't use an approved spot welder, we're using silicon bronze in a pulse mode to be able to control the heat. That way we don't change that metal.
And I think that's something that, is pretty unique to Honda, where they're doing it for, onto reinforcements and things like that, where a lot of the OEMs in the past were more cosmetic panels and things like that, where Honda was very concerned about the heat effect of those areas. And like you said, the spot welder arms can't get in there. The MIG brazing is an alternative that they call out. And sometimes it's a single plug weld, sometimes it's a two-hole slot. So you really have to pay attention to those repair procedures because there's some very little nuances that if you do the wrong thing in the wrong area, it's no longer going to be the specifications they want, and it could have an effect on the vehicle's crash performance in the future.
Absolutely. Honda has a great graphic that they've put out that shows a 1500 megapascal weld on a 580, and it actually fails on what should be the harder piece, all because we've changed that microstructure. So it is important. So some of the other things when we're talking about MIG-MAG, synergic controls. So in order to get to that spray pulse, we have to have what we call a synergic line. The right amount of voltage, the wire speed, and the gas coming together to get to that mode. Within modern machines, we can build that right in, so now it's on a button. Press the button, I'm in pulse mode, and I can adjust my settings and everything from there. Maximum welding current, again, so different OEMs have different specs that they're looking for. Programmability, again. We had an instance with Tesla when they first rolled out 4145 wire. Had never heard of it, went through the testing, were able to send it to our engineers, and 2 weeks later had a new weld program specific to that alloy. So this is all the capabilities that we need to be looking at when we talk about it. And then, again, power is another issue. So if you're running a welder on 3-phase versus single phase, it does have effect on the amperage, the maximum welding amperage. We want to make sure we're able to meet what that OEM is requiring. Okay. And then just the last, of course, it does apply to cosmetic dent repair as well. So when we talk about the heat sensitivity of aluminum, if you look at 10 different OEMs, there's probably 9 different annealing points that they allow you to work it with. And so it's important that we have that information and have equipment that's capable of handling it.
So I think one thing that I always, with any of the equipment out there, whether it's a spot welder, MIG welder, dent repair tools, it's the maintenance and changing out tips and keeping things clean, switching out liners on a MIG welder once in a while, not letting all that build up and get in there. Again, you can have the best equipment in the world. If you don't maintain it, if you don't take care of it, it's not going to be able to do it because it's going to have, if you have mushroom tips on your spot welder and that profile that's very specific, it's no longer going to be there. Those tips are only good for so long. And I don't know how many shops I've gone into and you look at the tips on the spot welder and they probably should have been thrown out 1,000 welds ago. And absolutely, that's, I think, something that is kind of a pandemic in the industry where they just are not paying attention to those little things that can have a huge effect.
Absolutely. So when you look at like the spot welding caps, different OEMs require different caps. They're looking for a different profile. Some of that's to work with the coatings that they have. So it is critical. That shape, the profile of it, is a critical part of the weld. Everybody thinks bigger is better. You flatten it out. We're not helping. We're actually spreading that energy over a larger area and compromising the weld. So absolutely. And maintenance is key. There are wear parts, there's consumables, and doing an annual maintenance on different things to verify that your cooling is up to, has been replaced, and all those things are critical. So, okay.
Well, I think that's We got it for the more? Okay.
So, just to wrap up, if we're relying on the OEM for the expertise in the repair, it only makes sense that we rely on them and trust them to approve the equipment that's going to meet their manufacturing and what they require.
All right. Well, thanks for coming out and sharing this with us, and have a great rest of your show.
Thank you very much.